Welcome to our class today, and we'll be looking at projection of a vector on another vector. Projection of a vector on another vector. So what do we mean by projection? Let's use this figure 2 here to understand what I mean by projection. Then we'll look at a few examples, of course the formula, and then a few examples. So I have this vector B here, and I have this vector A. So what is the projection of A on B? Projection of A on B. So what I mean is, supposing some light was to be put vertically above vector A, where will be its shadow on vector B? Where will vector A cast its shadow on vector B? So the shadow of A on B is what we call the projection of A on B. The projection of A on B. So if light were to be put vertically above A, its shadow will be this blue line. This blue line will be the shadow of A on B. So that is what we understand by projection. And this is how we write it. The projection of A on B. This is how we write it. Projection of A on B. This is a projection of A on B. And is given as the dot product of A and B over the magnitude of B square times vector B. So of course the projection of A on B and vector B are scalar multiple of each other, because you can see they are on the same line and facing the same direction. The same line facing the same direction. So say the projection of A on B is in the same direction as vector B, and therefore is a scalar multiple of B. But what is very important for us is this formula here, because we want to use it to do this example. The example is find the projection of vector A on B. We can also find the projection of vector B on A. And so we just change the formula. Just change the formula. Let's see what I did. And of course, we understand what the formula says. So the question was the projection of A on B. So by our formula, the projection of A on B will be A dot B over B square, magnitude of B square, everything multiplied by vector B. Everything multiplied by vector B. So let me just put the arrows above, because these are vectors. So this is what we mean by, this is what we want to find. A dot B over magnitude of B square times vector B. So what is A dot B? 2 times 2 is 4. So A dot B is just this. 2 times 2 is 4. Negative 2 times negative 3 is 6. And then negative 2 times positive 6. Negative 2 times positive 6 is negative 12. And that is what gave me negative 2. What about the magnitude of B square? Remember that the magnitude of B will be given by this. So when I square it, the square root sign disappears. So magnitude of B, 2 square will be 4. Negative 3 square will be 9, positive. and 6 square will be 36. So when you square the square root, the square root sign disappears. So that's why you have here 4 plus 9 plus 36, which is 49. So the projection of A on B will be given by this dot product over this square of the magnitude times vector B, which you can open the brackets, expand this, and get negative 4i over 49 plus 6j over 49 minus 12k over 49. So that's how you find the projection of a vector on another vector. So just as an exercise, try and find the projection of B on A. So using the same equations, find the projection of B on A. Let's look at another example. And the example is find a non-zero unit vector W that is orthogonal or perpendicular to this plane. Now this question is has two things to look at. The first thing that I'm looking at is the word unit vector. And remember that in our first video, we say that a unit vector in the direction, a unit vector first of all is a vector of length 1. So if I have vector u, the unit vector in the direction of u, in our first video we gave it as u over the magnitude of u. U over the magnitude of u. That gave us the unit vector in the direction of u. So what I'm saying is this question here has important things that it has. One is the word unit vector, and the other one is orthogonal. Orthogonal or perpendicular, they mean the same thing. And you remember that two vectors are orthogonal if their dot product equals to 0. So again, that one we covered in our video on dot products. So we say that vector A and B are orthogonal if their dot product is 0. So what does this question want? The question wants us to find a vector of one length that is orthogonal to P and Q at the same time. So we'll begin by finding just a vector which is orthogonal to P and Q, and then find one that has one length 1 later. So let's begin by first of all finding a vector that is orthogonal to both P and Q first of all. And then after that, we get a vector that points in the same direction as that one, that is of unit length. Now, so we need, let's call that vector omega 1, omega. Want that vector omega, we want it to be orthogonal both to P and Q. In other words, we want omega dot P to be 0 and also omega dot Q to be 0. Because if omega were to be orthogonal to P, then the dot product should be 0. And again, if omega is to be orthogonal to Q, then the dot product between omega and Q must also be 0. So I said let omega be xi plus yj plus zk. So in order that omega be orthogonal to P and Q at the same time, we must have omega dot P being 0 and omega dot Q being 0. And so that's what I do. I just get the dot products. dot product between this and this and equate to 0. So omega dot p will be xi plus yj plus zk dot I plus 2j plus k, and this is 0. So when I expand this, I get, and remember that dot product is a scalar quantity, so it will be x times 1, which is x, y times 2, which is 2y, z times 1, which is z. It should be 0 because omega dot p is 0, so this should be 0. And again, since omega and q must be orthogonal, their dot product must be 0, so their dot product will be given by this. So x plus dot 2 will be 2x, y dot 5 will be 5y, and z dot 4 will be 4z, and this should be 0. So I have these two equations, and these two equations we can solve them using simultaneously. We can solve it simultaneously, or we can solve by reducing to echelon form. So I've said that these two equations can be solved in several ways, like reducing it to echelon form or just solving them simultaneously. So I decided to solve this equation simultaneously. And let's see how we solve them. Although you can also solve it simultaneously but in a different way. So look at the way I did it. The way I did it, I said that I took z the other side. So this was, remember, this was 2x plus 4y equals to, no, plus z equals to 0. So I took z the other side. So this is what I got. And this was 2x plus 5y plus 4z is equals to 0. So I took 4z the other side. And this is what I got. So at this point, what I did was I wanted to solve this by elimination. So when I subtract equation 1 from equation 2, subtract this from this, I would have y equal to 3z. Let me see. Because it will be 2x plus 5y equal to negative 4z, and this other one is 2x plus 4y equal to negative z there. Then I subtract, I have y equal negative 3z, y equal negative 3z. Just check, first of all, the equations. Yes, they are okay. That is what they were. So when you take y, z the other side, this was, yes. So what let me just carry the equations. The equations were, let me just carry the equations first of all before I do this. Just carry them first of all so that you see what I did. Let me just delete this. So just before this, what I had was x plus 2y. Let me just see. Let me just go back and see. Yes, it is. It's down here. It's down here. Just write it. It is x plus 2y plus z equals to 0, and 2x plus 5y plus 4z equals to 0. So let me just be sure that I'm carrying forward the correct equations, and then let's manipulate them. Okay, so what we had was x plus 2y plus z is equals to 0. That means x plus 2y is equals to negative z. Got it? Good. So that is where maybe I went a mistake here. And this other one was 2x plus 5y equals negative 4z. Good. Now, so what I did at this point, I wanted to eliminate x. So this is equation 1, this is equation 2. I decided to multiply this equation 2 by 2. So when I multiply equation 2 by 2, I get it 2x plus 4y equals negative 2z. And this other equation is just 2x plus 5y is equals to negative 4z. So subtracting these two equations, this would give me 0, and this would give me y equals, and this would give me negative 2z. Negative 2z. So y is negative 2z. So the only mistake is here. This one is supposed to be negative 2z. Negative 2z. So that this y is this. Good. Now once I get y as negative 2z, what becomes of my x? So I go back to this equation and make x the subject. So x is negative z negative 2y. But we know what y is. So x becomes negative z negative 2, but y is negative 2z. So that x becomes negative z plus 4z, which is 3z. That's why you see that my x was 3z. Good. So what is our vector that is orthogonal to P and Q? Our vector W omega was xi plus yj plus zk. But we already know what x is. So that means our omega will be 3zi minus 2zj plus zk. This is omega. And that is what I had here. 3zi minus 3zj, no, 2zj plus zk. And this we can even factorize because z is common. And this will be 3i minus 2j plus k. So this is our omega. The question wanted a unit vector that is perpendicular to P and Q. So we can obtain that by getting a unit vector that is in the same direction as omega. A unit vector that is in the same direction as omega would be omega over the magnitude of omega. And that's what I did. This is omega over the magnitude of omega. Remember, omega is this. So the magnitude of omega is that. And so let's just do that and see if I have those correct figures. So what is the magnitude of omega? So the magnitude of omega would be the square root of, just a minute, the square root of, I'm just getting the magnitude, just the magnitude of omega. The magnitude, just a minute, right? Then it's not writing here, but the magnitude of omega will be the square root of z square into bracket 3 square will be 9, negative 4 square will be 4, and negative 2 square will be 4, and 1 square will be 1. So this will just be z times square root of 14. Good. So what this means, this is now the magnitude of omega z root 14. So when I take z 3I minus 2j plus k and divide by z root 14, the z's cancel. So I'm left with 3I minus 2j plus k over root 14, which you can simplify to get this. Can you simplify that to get this? And so that is how I do this question. That's how I get a vector that is unit vector. And I say from the beginning of the question that it's very important to note that this question had two words that are very important, unit and perpendicular. So we use those two words to do the question. Now, so thank you, and next time we'll look at another concept in vector analysis. And remember to subscribe to get more other free videos.